Hello everyone, I am Hassan Hassan. I'm a grad student from Marshall University. The title of my poster is Empagliflozin relaxes resistant mesenteric arteries by stimulating multiple smooth muscle cell voltage-gated potassium channel. Empagliflozin is a sodium glucose cotransporter 2 inhibitors. It is a new class of antidiabetic drug. It acts in the kidney and inhibits this transporter, reducing the reabsorption of glucose, thus reduce the blood sugar level. But recent study shows that it can also reduce the blood pressure, but the mechanism is still unknown. So the objective of this study is to investigate the direct effect of empagliflozin on resistant arteries, especially mesenteric arteries, and also to dissect the underlying mechanisms. We use pressurized arterial myography to generate data for this study. Figure 1 shows the setup. Panel A is the instrumentation, panel B shows the microdissection tool, panel C shows the mesenteric bed under the microscope, and the panel D is a representative pressure myogram. So coming to the results, figure 2, panel A, B, and C shows that empagliflozin can dilate the myogenic mesenteric artery in a dose-dependent manner. And figure 3, panel A and B shows that empagliflozin can reverse the phenylephrine pre-constricted artery. Similarly, it can also reverse the thallic-mediated pre-constriction of the mesenteric artery as shown in panel C and D. So coming to the underlying mechanisms, we initially focused on the nitric oxide soluble guanyl cyclase and PKZ signaling pathway. Figure 4, panel A and B shows that using different modulators of the inhibitor of the signaling pathway has no effect on empagliflozin-mediated response. Similarly, inhibition of the prostacyclin synthesis by indomethacin, as shown in figure 5, panel A and B, has no effect on empagliflozin response. And finally, in figure 6, shows that denudation of the endothelium has no effect on empagliflozin-mediated vasodilation. Panel A and B shows the successful denudation, which is confirmed by the absence of the acetylcholine-mediated dilation. Whereas panel C and D compare the empagliflozin response in the endo-intake and endo-denuded artery and shows that there is no difference. So we focus on the smooth muscle-derived signals. So initially, we use the non-specific inhibitor of the voltage-gated potassium channel. As shown in figure 7, panel A and B, the non-specific inhibition of the cavity channel caused the significant reduction in the EMPA-mediated dilation. Panel C and D shows that specific inhibition of the Kv 1.5 by DPO1 and the Kv 7 by linoprorodine significantly reduced the EMPA response. Not only that, the inhibition of the Kv 1.3 by SORA4 has no effect, but the dual inhibition of Kv 1.5 and Kv 7 has more significant effect than the individual agent. So ultimately, we can say that empagliflozin-mediated response is caused by the activation of the voltage-gated potassium channel. We also check the involvement of the calcium-activated potassium channel and the ATP-activated potassium channel in a smooth muscle by using pegzilin and the glibenclamide, which are the inhibitor of those channels respectively. And figure 8, panel A and B shows that there is no difference, and there is no significant difference in the response. So overall, we can propose the mechanism is empagliflozin can activate potassium channel, causing the flux of potassium, causing hyperpolarization of the smooth muscle cell, resulting in the vasodilation. So overall, in conclusion, we found that empagliflozin dilate the mesenteric artery. That doesn't involve the endothelial signal like nitric oxide, cyclic GMP, or PKG, or prostacyclin. Rather, it involves the smooth muscle voltage-gated potassium channels, mainly Kv 1.5 and 7, but it doesn't involve the BK or the KTP channel. In future, we are planning to do the similar work with canagliflozin and dapagliflozin, who belongs to the same class of drugs. Not only that, it is also important to check whether this kind of dilation can result in reduction of the systemic blood pressure. This study was supported by a startup grant from the Marshall University College of Pharmacy to Dr. Rakibul Hassan. And finally, there was two questions, how this could relate to the real world or how it could benefit in the COVID situation. As I told you, empagliflozin has a multifaceted benefits. It can reduce blood sugar. At the same time, it can take care of some of the comorbidities like hypertension or cardiovascular abnormalities. So obviously, it can help people who has those kind of situation. Not only that, for the COVID patients, if they have the underlying situation, they are more vulnerable to the severity of the COVID. That's why this drug can be used as a COVID treatment. And in fact, one of the research group in Oxford University are trying to develop empagliflozin as a COVID treatment. With that, I'd like to thank all of you for listening to my presentation. Thank you.